Okay, we're back, and in this case, we're looking at the mathematics of calculus, and in particular, we know how to do derivatives. We've done that first, and that is basically, think of derivative as a fancy word for the slope of a tangent line. And there's this cute little rule that we have, at least for polynomial type terms in an equation. So if we have a function where you have a constant times x to some power, we can do a derivative by the shortcut. And we kind of came up with this in terms of finding slopes. Okay, just a normal slope equation. We take a limiting type process where the 2 points on the curve get very close together, and they provide us the slope of the tangent line. Practically, what we do that in physics, we're starting off with this idea of being able to find things like velocity and accelerations. Velocity now is, by definition, the derivative of position with respect to time. Acceleration is the derivative of velocity with respect to time. Okay, these are rates of change. And we know from motion graphs that velocities and accelerations are slopes of different types of graphs. Now the question becomes, often, the one thing that we know is acceleration. That's our starting point. And so if acceleration is the derivative of velocity, is it possible to take that derivative and somehow undo it in order to find out what the velocity is? And once you have the velocity, is it possible to undo this derivative of position to find out what the position function actually is? And obviously we wouldn't have this video if it wasn't possible, so we called that an antiderivative. Eventually we'll call this thing an integral. Okay, it's kind of a fancy word, but we're going to try to figure out what that means. And if we know how to do both derivatives and antiderivatives, it won't matter what we're given in a problem. We will be able to figure out everything else about the motion. Okay, now it turns out that to do antiderivatives, it's very much related to areas below graphs. So think about a couple types of graphs that you know about. Okay, here's two examples of a velocity versus time graph. This first one on the left is representing a constant speed. And you could ask the question, well, how far, let's say if that speed is 3 meters per second, and you have this thing rolling at a constant speed for, 3 seconds, just make this up. How far does it travel? Well, it turns out that the distance is velocity multiplied by time. So you'd have 3 meters per second times 3 seconds, and it would be 9 meters. But now, is there a connection between that math and this graph? And perhaps some of you see it right away. The area of this graph is an area of 3 meters per second times 3 seconds. It's base times height. Okay, which will give you 9 meters of area. Even the units work out on the graph. Okay, now identify this graph on the right. You have a straight line on this velocity graph. Well, by knowing derivatives, if you have a constant slope on a velocity graph, that means you have a constant acceleration. And we also know that, check this out, if we have a certain amount of time down here, and we think of the shape of the graph, it's a triangle. Now we know that the area of a triangle is 1/2 times the base. Well, the base is just however many seconds you have, that's the time. And what's the height? Well, if this is constant acceleration, the height is whatever your final speed is right here. But we know from kinematics that we've got this little expression for constant acceleration for final speeds. And if we assume, in this case, if your initial velocity is 0, then your height, okay, your final velocity is acceleration times time. Well, plug that into 1/2 base times height. The height is AT. And here you get 1/2 AT squared is the area of that triangle. What else is 1/2 at squared? Well, for constant acceleration, that's the distance that you travel. So areas mean something. Okay? Areas can actually give you physical answers depending what quantities you're plotting on the graph. Alright, well, those are fairly simple. Rectangles and triangles. Okay, those are shapes we know how to find the areas of very quickly. What if you have a curve, though? This is where the trouble starts. How would you find the area below a graph like this, where you have a curve? Okay, that became a dilemma way back when. And here's kind of a way they started to figure this out. If anything, we can at least approximate the area. And how might we do that? There's a few ways you might dream up, but kind of the standard way, I guess you could say, is imagine you... Let's make use of the fact that we know how to find areas of something like rectangles. You could take a rectangle and put it there, and then you could take another rectangle and put it there, another rectangle, put it there, and so on. Just keep filling this up with a bunch of rectangles. And it could be the sum of the areas of all those rectangles. Okay, well, let's see. Let's jazz this up a little bit. For simplicity's sake, let's say that each little rectangle has the same width. Let's just call it delta x for lack of a better term. And the height, okay, for any one of these rectangles is whatever the y value is of some point on that curve, on the parabola. Okay, so the base is delta x, and the height is the y value, but we know the function. Okay, so the y value is x squared. Okay, so if we add up all these little areas for each of these individual rectangles, we can get an approximation. Now obviously it's an approximation because we're missing area between the rectangle and the curve. Okay, so the question is, how do you make it a better approximation? How can you reduce that area that we're missing? And perhaps you see it, what if instead of wide rectangles, let's erase some of those, what if we made a bunch of skinny rectangles? Now with skinny rectangles, you start to fill in some of that missing area. And the way you make a skinnier rectangle is you basically start to make the width a little skinnier. Okay, that delta x. So kind of like it's the same idea that we had for derivatives and slopes. If we go ahead and really make these things incredibly skinny, make that delta x get closer and closer and closer to 0. You go from an approximation of the area to the exact area. And the notation that we have for this is if we do the limit as delta x gets really small, okay, if these rectangles get really skinny, on our height times base, okay, whoops, and then we're doing the sum of all that to get the total area. This should work. Okay, now again, that's a lot of notation to write. I don't have to keep writing these limits down every time I want to do this for any kind of curve. And so, you guessed it, we have a symbol for this. It's kind of a funny looking S. It's a Greek symbol summa, meaning sum. And instead of a delta x, it's kind of like what we do for derivatives, we change the delta into a d. This is notation. Whenever we see this new symbol here, this tells us that we're going to have to find an antiderivative of whatever the function is that we're using. Okay. Now in this case, let me change color slightly. Our function is x squared. Okay, now what I'm going to do is just go ahead and write down a shortcut of how to find an antiderivative. We're going to be doing this for now just with the same types of functions that we have for derivatives. Okay, and whatever this function is, in order to be able to find the areas, it turns out we have to find the antiderivative of the function. Okay, and our rule is going to be whatever the constant out front is, okay, that coefficient. Now let's see, if I recall correctly, when we do derivatives, we have to subtract 1. Well, if you want to do an antiderivative, it probably makes sense that we're going to have to add 1. And now we're going to divide by new power. Okay, now we can check to see if this works, because if this is an antiderivative, then if we do the derivative of this thing, we should get back what we started with. And so let's apply our rule to this thing. If you haven't seen this before, I know this might look kind of weird and goofy. But our rule says take the power, well, the power is n plus 1, multiplied by our constant, subtract 1 from your power, where n plus 1 minus 1 is just n. And this is all over the n plus 1 that we had. And lo and behold, you get back what you started with. Okay? So this little shortcut rule right here is what we're going to use. It works. Okay, let me just do one quick example. Let's suppose that the acceleration function that we're given is, again, I'm just making this up, 3 times time to the 4th power, some crazy force and acceleration that you have on an object, plus 3t minus 2. Okay, looks as good as anything. How would you find out what the velocity is? Well, acceleration is the rate of change of velocity. And if you want to solve for the velocity up here, how would you solve this equation? Well, that little bit of velocity on top, we can take the time and bring it up. Velocity is acceleration multiplied by time. Okay, these little dv's and dt's, we can treat them just like an algebra, like a little variable. And then if you want to get your actual velocity, we have to undo this derivative. We have to use this symbol, which means you have to do an antiderivative of your acceleration. So if we plug in the function that we have, 3t to the 4th plus 3t minus 2, we can use this rule that I just wrote down, term by term, and figure out what our velocity function is. So this first term, I'm going to add 1 to the power, so I get t to the 5th power, and then divide by the new power, which is 5. We add 1 to this power, this is time to the 1st, so we have time squared divided by the new power. Now what do you do for a constant? Minus 2. Well, if we think of that as time to the 0th power, we can add 1 to the power, so we get time to the 1st divided by 1, which is that new power. And this would be your velocity equation. We could do an antiderivative of this to get our position. Okay, so here are the first term. We have 3/5 as our constant. We're going to add 1, so we get time to the 6th power now, and divide